Welcome back to our series of solution and explanation to competitive coding. Today we are going to solve LeetCode question number 104, that is maximum depth of binary tree. Okay, so I think so the title of the question is self-explanatory type of question. We have to find the depth of binary tree, okay, maximum depth. So let's read the question and understand what the question says. So given the root of a binary tree, return its maximum depth. Okay, so we are like given the axis of root of some binary tree and we have to return like the maximum depth of that binary tree. A binary tree's maximum depth is the number of nodes along the longest path from root node down to the farthest leaf node. Okay, so they describe depth as like a if you have to find or calculate the depth of any binary tree, so we have to go through and count all the nodes from like root node to furthest leaf node. Okay, the leaf node which is like as maximum far as possible from the root node. Okay, and the like inclusive of a root node and that leaf node, the number of nodes which appear in that path is the maximum depth of that binary tree. Like in this example number one, if like this is the structure of the tree, so if we go to calculate like for the like left of root, then the depth is like only 2 because the path from like root to leaf contains only 2 nodes, that is like root node and leaf node. If we go for the right of the root, then we can find that it will return us as 3 of depth because it has like 3 nodes from root node to leaf node. This path contains either of this path, like from right to left or right to right. This path contains 3 of nodes, like one root node, one intermediate node, and one leaf node. Either of the path will contain like 3 nodes in the path, so we have to return the maximum of that. So in this case we have to return 3 because like maximum depth is 3 or the greatest height is 3 for this tree. And in our second example there are only like 3 nodes. One is root, that is 1, that holds the value of 1, and left child is null, that is no node at left, and the right child is 2, that is 1 node at right. Okay, so the maximum depth or the maximum height that our tree has is 2, that is 1 root node and 1 right child. Okay, so we have to return 2. So there are some constraints. The number of nodes in the tree are in range from 0 to 10 to the power 4. Okay, so the nodes could be something like 0, between something 0 and 10 raised to 4, and the value of nodes are like from -100 to 100. Okay, so let us jump to our explanation board and see how can we solve this question. So suppose this is our example binary tree on which we have to calculate the maximum depth. So basically we have to calculate depth by doing like leveled order traversal, or BFS we can say, to like calculate the maximum depth. Like we can start from root and we will go to our furthest leaf to calculate the height. So this could be done by leveled traversal. It could be done by DFS, but DFS and BFS both will work in the same way because we have to traverse each node to get to the farthest leaf node. Okay, so we will go do it by BFS or like level order traversal. So level order traversal could be done in 2 ways. Like we could implement it by generally we implement BFS with the help of queues, and it could also be done by recursion. Like level order traversal could also be done by recursion. So when to use queue and when to use recursion? But when your tree is skewed, or whenever our tree is skewed, then we should use our queues, because if our tree is skewed, then we need lesser amount of queue, like lesser memory or lesser space in our queue to put the nodes and then retrieve those nodes and put the other or child to those nodes to do level or traversal, so that we need lesser amount of memory to like put the nodes and then put their children if our tree is somehow skewed. But if our tree is like a kind of full binary tree, then it will take almost order of n space to put the child, like put the leaves of the tree, because there are lot of childs in the tree leaves. So it would take something around out of n n size to put the leaves. So if we have like a child which is something which has structurally similar to complete binary tree, then we should use recursion. So generally trees are not of skewed style, so we are going to use recursion in this solution. So recursion, by recursion we can also do in two ways. Like we could do recursion in two ways. Like we can do like in top down approach, that is top down approach, and we can also do it in bottom up approach. In top down approach we could do is like when we meet any node we have to increment its height. Okay, so when we go to root node we'll do a mark as its height as 1, and when we go for its first left child and we meet another node then we increment its height by 1, that is it will become 2, and then we again go to its left and then we mark it as 3, and then we try back and go for its right, then we mark it as 3 because it is 2 plus 1, and then we do this in the same manner. But in BFS what we could, like in bottom up approach, what we could do is that we have to like calculate the height from bottom to top. That is, there is a function we can do is that we can return like 1 plus max of whatever the root returns, like max of whatever the left or right child returns. Let me explain this so that it would become more clear to us. Okay, so what I'm trying to say is, suppose this is our tree, this is our example tree, so and we have to traverse it. Okay, so when we are here we could say that height of this root or height of this like node is whatever the maximum height of its children, either of right or left child, and plus one for this node. Okay, one for this node, and whatever the maximum height is either provided by its left child or right child. So we start traversing its left and right child. So we move it to its left and we find again we have left, then we move to its left, and when we again we found its node, and then we move to its left, and finding null value. So whenever we find null value, we are going to return 0, because null means there is no node, so we don't have to increase our height. So whenever we find null value we are giving 0 as returning 0 as value. So this node will return 0 to this node, and now this node will do is 1 plus, that is 1 for this current node, plus whatever the maximum of left or right child will provide us. So for this node, left and right both child will provide 0 as return value because they are both null. So it will do 1 plus 0, that is max of 0, and 0 is 0. So this node will now return 1 as value, and now this node will similar is the case for this node, both the left and right child will return 0, so it will also return as 1. And now maximum of 1 and 1 is 1, so this node will return 1 plus 1, maximum 1 plus maximum of 1 and 1, that is 1, so it will return 2 as maximum value. Now we will go and check for like right of root, then this will call this node, and this node will call for its child, and this node will call for its child. Again similar situation, left and right are null, so this node will get both the zeros, and it will return like 1 plus max of both zeros, so it will return 1 plus 0 is 1. So this node is going to return 1. Now this node has again choice, this like its left is returning 0 as value and its right is returning 1, so it will choose max of both, and it will add 1 to it. 1 plus 1 is again this. Now this node is going to return 2 as return value, like its height value, and now again this node is getting 0 from its right and 2 from its left, so it will choose max of that is 2, and now it will add 1 to it, that is it will do 1 plus 2, and it will now return 3 to its parent. Now we are getting like 1 plus 2, we have to return 3. Okay, so it is 1 plus 2, it will return 3. So now we have to choose from 2 and 3, which is maximum. Now 3 is bigger in both the values, so this like root will return 1 plus 3, that is 4, and that is the height of our tree. We can check like from root to this node we have 4 nodes. There are 4 nodes appearing in this path, so the height of the tree is 4, so the root will return 4. So this is the basic idea what we are going to do, and let us now code this solution so that you can understand in more clear way. So first thing we have to check if like in each case, if our root is empty, root is null, then we are going to return 0 simply. And but now we are going to traverse for left and right child. Oh, okay, int left, it will become whatever our function is, we are going to call it recursively. Then I'm going to call it for root dot left, and I'm also going to call it for right, then it will become root the right. Now I have called it for like it's left and right recursively. I'm calling for both the values, and finally I have to return 1 plus whatever the max of left or right will give us. So I'm going to do 1 plus math.max from whatever like left or right we get, left or right, whatever we get maximum, we are going to return that. So I hope this solution should work, and let me check if it works or not. So it did work. So let me submit our code to check if it is valid for all test cases and if it is optimal or not. So it seemed to be an optimal solution, and so it is 100% faster. That means the sense of time complexity it is doing very well, but for space complexity it is like only 15% better than other solutions. Why? Because we are using like a double recursion, and recursion uses auxiliary memory, so that is why it is consuming much of space. Hope you understand the concept and enjoy learning, and if you have better solution you can comment in the comment section down below. As always, thanks for watching.